Welcome to today's Manufacturing Engineering Media webinar. Our topic is Advancements in Robotic Laser Welding and Cutting. Hello, I'm Jim Sawyer, Senior Editor at ME Media. Before the presentation begins, I'd like to provide some background on what we will be doing today. Our sponsor, ABB Robotics, is a business unit of the ABB Group. The ABB Group is a leader in power and automation technologies that enable utility and industry customers to improve performance while lowering environmental impact. Our presenter, Jorge Isla, is Global Technology Manager for Welding and Cutting, ABB Robotics. He specializes in robotics offline programming through ABB's Robots Studio software, welding, cutting, and automation. Jorge has worked with ABB Robotics in various roles over the last 15 years. During the presentation, you will be able to ask questions which Jorge and his colleague, Jeremy Wisdom, will answer once Jorge wraps things up. Simply use the Q&A box that will appear at the bottom of the screen. If time runs out before we can get to all the questions, we will make sure the answers are emailed to you. Also, if you have any questions about the workings of this presentation or any aspect of ME Media's webinars, please email me at jsawyer@sme.org. I'll rejoin you after the presentation with a few concluding remarks. Now, welcome to Advancements in Robotic Laser Welding and Cutting. Jorge, it's all yours.
Thank you very much, Jim, and welcome everyone. Thank you for spending the time with me today. And I'm assuming that everyone in the line understands the concept of laser processing. So I am not going to go through the application itself, and on the other hand, I will be talking about robotics and what we do in ABB. Robots and the laser technology nowadays are becoming more and more efficient. Improvements in that area have been achieved over the years. In ABB, we have been delivering systems since year 2000, more or less, and we are very proud to say now that robots are more accurate, are better, and laser technologies are more accessible in terms of pricing, serviceability, etc. So I will be covering all these topics today, and as Jim mentioned, you will be able to send me questions, and we will make sure to answer everything. The applications we are focusing nowadays in the robotic laser cutting and welding is the automotive and general industries. In the automotive, we see a trend of the use of light and exotic materials in order to reduce weights of vehicles and reduce gas consumption. And therefore, they are forced to use lasers for both applications, welding and cutting, due to the fact that they have to cut stamped steel, hot formed steel, hydroformed parts, and in the general industries, they are also in the need of replacing applications like plasma cutting and oxy-fuel cutting. And everything is trending into this fascinating technology of robotic laser applications. There is a market where we are introducing robots, and we are competing against what we call hard automation, which are dedicated machines from 3 to 5 axes. And you can say that these are different animals. The robot is based on joint axes that are a little bit more difficult to control, rather than the 5-axis machines that are based on prismatic axes easier to control, and faster. So we have to make that differentiation. And that brings us up to the fact that robotic laser processing can go up to a 30% lower in capital investment. You have a reduced floor space too, the possibility to eliminate existing operations like presses, reminding you that maintenance costs for dies of these presses are really high, and basically you have to work through them every 20 cycles, 40 cycles, depending on the application, the product, and the material they are processing. So robotic laser cutting in this case is the answer for these manufacturers. Productivity and quality are also comparable to these machines. Robotic processing is a little slower than a 5-axis machine, but we see this trend in the automotive industry that is accepted, and they are sacrificing some of those cycle times and quality that has been improved with robotics. The operational efficiency is also being increased over the time. We can work generating offline programs through our Robot Studio software, which is an offline programming and simulation tool. You are able to have fast and accurate tuning calibration for motors in the robots. And the flexibility that the robots are offering is also important to highlight. If you invest in robotics, you have the ability to reprogram paths. You can take those robots out of a laser processing area and use them for material handling, for assembly, for picking, packing, palletizing, etc. So you just replace the end effector and have the flexibility to reuse those robots. Now, when it comes to robotic laser, there are important considerations to take into account. It's not just that any robot out in the market will do the job. With laser cutting and welding, you're looking for precision and repeatability for paths and have a better processing and quality. So robot rigid arm construction is really playing an important factor here because it allows faster reposition times due to the absorption of kinetic energy. And I will go through details throughout this presentation. So all these bullets you see in this slide will be covered in detail. But if there is anything else more in depth that you want to have information about, you see my email address at the bottom of the screen, and you are free to contact me anytime. Safety is also an important factor. Lasers are dangerous equipment, and we have to encapsulate the laser beam into a light, tight enclosure so the operator is working in a safe environment, and people transiting in the manufacturing area are also protected of these hazards. When it comes to the robot, we have the motion planner, which is software to control the robots, the 6-axis. Our arms are 6-axis machines. And what we are doing with that is that we are transducing robot positions into paths. And those paths have been improved over the time with different generations of software and motion control. The tool has, or the head, the laser head has a weight that has to be taken into account for the robot to control the moments of inertia, acceleration, deceleration, and we have to be very accurate on calculating that weight, on calculating the centroid and moment of inertia of those tools. The arm load, which is part of the dress pack, has also to be considered in order to avoid overshoot of the robot while it's following paths. The dress pack plays an important factor here because it will be pulling the head in certain positions that the robot is going through the working envelope. So a hose package that holds the fiber, the cooling hoses for the head and the fiber have to be also taken into account, signal cables, and you will see pictures throughout this presentation on how we solve those issues. The programs are based on what we call the TCP, which is the tool center point of the robot. And those TCPs have the ability to be calibrated manually. That means a programmer can jog the robot to different positions with his hands and the flex pendant of the robot and using his eyes. But that is not really what we want to do in laser applications. We really need to have an accurate TCP, and this measurement is done automatically with one of our peripheral equipment called Bullseye, and you will see more information about it. If we are to manipulate the processing part, we use external access to the robot, which we refer to positioners within ABB. And the calibration of those external access has to be also done automatically. We try to reduce human errors as much as possible. The robot consists of gearboxes and motors, and like any other equipment in this nature, we have friction, and that friction is affecting acceleration, deceleration, paths, and the performance of the robot. And every motor and gearbox is unique, and we have to automatically compensate for those frictions along the path that has been programmed. And in ABB, we have this automatic tool that is very efficient too. When it comes to programming, you don't want to do that online neither. You want to have accurate paths, accurate geometries and features, and that has to be programmed offline in the comfort of your office or sitting on an airport or wherever you are in the world. You can basically bring in 3D CAD data and start programming offline. There are also additional optimization tools. So if we see that the quality of the shapes we are getting in the manufacturing floor are not as accurate as we want them to be, we can use offline tools also to optimize the path of the robot. And last but not least, experience and best practices. I already mentioned that ABB has been delivering laser systems starting in the late 90s throughout the world, and that experience has been helping us to improve areas like in the dress pack, software and motion. When it comes to rigidity and the robot itself, we are introducing two robots into our cells. It's called the IRB 2400 and IRB 4400 with different handling capacities and reach of the arm. So we select these robots based on the customer application, the size of the parts, etc. Both can be used for both applications, either welding or cutting. We use a link arm into these robots. That is helping us also to maintain better path performance. And that is linked, of course, to our motion control software, what we call True Move and Quick Move. Robots and any other machine tend to cut in corners. It's like when you're driving your car and you slow down on a curve for safety, the robot tries to do the same thing. But thanks to True Move and Quick Move, which are just internal names in ABB to differentiate our software, we are able to maintain speed and positioning all along the program path. Our robots are made of steel, cast steel, and that makes also the arm more reliable and efficient and stable. If we are to manipulate the processing part, we have different configurations of what we call the positioners. It can be rotated in horizontal axis, and of course you want to have the robot processing at all times because you make money if the robot is processing. If the robot stands still, you're losing money. So you want to have a two-axis positioner, so while the robot processes the parts, the operator can be on the other side of the station loading and unloading parts. For this matter, we have different positioner configurations that allows us to handle different payloads and sizes of parts. And we have what we call a Ferris wheel positioner, which is K. We have a vertical index station, which is the R positioner. And those two can manipulate the part at the same time. And the other one is the IRBP-C, which is just a turntable with no axis manipulation of the part. And all these positioners are servo-controlled and built in the same system as the robot. So you can call a robotic system of 6 to 7 or 8 axes, fully coordinated. Our cells are also named after the name of the positioner. So we have the robots, the 2400, 4400, and the positioners give the name of the cell. So for laser cutting processing, we have laser cut U2 with fixed stations, laser cut K based on the K positioner, R for the R positioner, and C. We're also very proud of our software offer, and for that matter, we have two different software packages. One is called Robotware Coding, which is a controller-based software working on the real robot, and in the offline environment, we have a Robot Studio Power Pack, which is an add-in to the basic application of simulation and offline programming. Within our product offer, of course, we have training here in our facility in Auburn Hills. We have a training lab available for customers and projects, and we have this training open for everyone too. And of course, we have a full network of global service and support for not only laser applications, but any other robotic related application. When it comes to the TCP calibration, as I mentioned, we have to make sure that we have an automatic tool that generates an accurate TCP. And you see that repeatability of this TCP has to be less than 0.1 millimeters. So it's a very accurate machine, and it's fast and reliable. It calibrates also the Z directional angle, which will later on help us in programming to make sure that the laser head is normal to the surface that we are going to process. Very important in both welding and cutting applications. And the important factor here is that it's eliminating human errors. In this picture, you see an example of a dress pack that has been evolving throughout the years. We are separating the fiber from the rest of the cable management, and that is for serviceability reasons. if the fiber gets damaged, you don't have to dismantle the complete dress pack. Instead, you just pull the fiber through its single hose and put a new one, and basically you're up and running within minutes. The water lines and the communication lines to the head are separate in a bigger hose. Those are less sensitive for failure and therefore are separate in a different line or cable conduit. Partner collaboration is also very important for any project. And we in ABB have standardized packages where we partnership with companies like Fronius, which has a very mature and advanced package for laser hybrid welding, where you add cold wire to the pool, the weld pool, and combine it to the laser processing. When it comes to generators, we use basically IPG, Trump, Ruffin, but that doesn't mean that we only work with these companies. It's just that we have a more mature approach and packages with them. And Precitech is also a supplier of robotic head equipment for laser welding processing. In this slide, you see a couple of pictures with different head configurations. You see a laser mech product offer where the fiber optic is coming from the top of the head. It's a straight head, what they call a 0 degree, or it can be also coming from the side of the head on a 90-degree angle. And we use simulation tools, Robot Studio, in order to determine which head is the best for the application. We have to take into account accessibility to the parts and possible collisions between the fiber and clamping equipment or the tooling or the part itself. So depending on the application, we select the head, of course. And Precitech has also very mature products. In this example, you see a picture with a 100 millimeter collimator, 100 millimeter focus optic. And both heads, by the way, Laser Mech and Precitech, have capacitive sensing that is helping us to control the head on the Z axis. When it comes to software, as I explained, we have robotware coding is what the real robot controller is running, where you have predefined user interfaces and HMI screens for the operator and the programmer. You have a easier interface for shape generation, equipment classes, as I mentioned, Fronius, Trump, Ruffin, IPG. And it gives us also the ability to have the advanced shape tuning for friction tuning compensation, which is automatic. You just set the robot into a learning mode after the program is done for the first time. We let the robot learn the friction that is reading in every servo of the robot, and feeding the information back to the controller, and starts doing iterations to compensate on the friction of those servos. And we also have another portion, software portion called ILC, which stands for Iterative Learning Control, which is going to help us to improve shapes. Probably the most challenging shape in laser processing is a circle, where we program a perfect circle in an offline environment, but when the robot is performing the motion, then you start to get egg shapes or ellipses or things like that. So ILC is reading information from the real controller, from the servos, feeding the information back through the axis computer of the robot, and we start to iterate and make adjustments in the path as the robot moves. The Robot Studio Cutting Power Pack, the offline tool, which helps us to simulate and calculate cycle times in an offline environment, with predefined tools also for different features and shapes for cutting specifically. And I already talked about True Move and Quick Move, which makes the robot maintain the TCP speed and do not cut in corners. But we also have what we call wrist move, which is basically locking the rest of the axis of the arm. So the wrist is free, axis 5 and 6, and we primarily use this option for small features less than 6 millimeters. If you think about a 6 millimeter circle in diameter, we try to use wrist move as much as possible. And a good analogy, by the way, in this case is if you yourself are to draw a circle with your hand and you extend your arm and try to draw a circle, you will be less accurate as if you just rest your wrist above the paper and draw the circle. You will be much more accurate than extending the arm. And that is physics, and that applies also to the robot itself. Bullseye I explained already, that is an automatic tool for calibrating the TCP. And absolute accuracy is a robot option that we always use for laser applications, where we are compensating for deflections on the arm. When you have the robot equipped with the laser head, of course, the upper arm, the natural thing that happens with the arm is that it sags because it's having weight at the end, and there is a moment on the axis that is sagging the robot. So we measure that robot in a special area, special booth with a laser equipment, by the way, and we start compensating for those sags and trying to achieve an absolute accurate motion. That's what the robot is going to perform. In this screen you also see the flex pendant, or the programming unit, with an HMI showing graphics in a color screen for the operator to interact, and also for the programmer to make programs online if it's required. Remember that I said that we program all these robots in an offline environment to be more accurate and have better quality, processing quality. So we have predefined 2D shapes. We have an auto shape tuning integrated with code instructions, meaning that the robot instructions are taking care of the motion itself, but we also have arguments within those instructions to control the laser equipment and have the ability to shape and tune the process. We have the HMI. We have speed modulation. The robot will tend to slow the TCP speed in corners, and even when Quick Move and True Move is trying to take care of all those issues, natural issues, we have the ability to modulate the power as the robot is moving, meaning that if the robot is slowing down the TCP speed on a corner, we have the ability to reduce the laser power also and try to eliminate as much draws as possible and increase the quality of the cuts. These HMI screens are delivered by ABB, but robot programmers and our customers also have the ability to customize these HMIs by themselves. You don't have to be a rocket scientist or a C# expert in order to create these HMI screens. We have a product called Screen Maker built in Robot Studio, which gives you the ability to drag and drop different tools like buttons and screens and information boxes into the Flex Pendant area and start programming and creating these HMIs in a very efficient way. When it comes to shape generation, we are making a trend here in robotic processing. Traditionally, in order to program a circle, the robot requires 4 targets that are interpolated between each other and achieving a circle. But that's not really the way it should be handled, and therefore we changed the nature of that programming part, and we are only focusing on the center of the circle and any other shape. Here you see slots, you see rectangles with radiuses, you see the circle, where we program the center of the feature, and then with parameters like radius and sizes like height and length, we control the shape in a more accurate way. And those predefined shapes are circles, slots, rectangles, hexagons, and free-form CAD shapes that can be programmed. For example, a keyhole, very popular in the automotive industry to insert cable harnesses, holders, etc. The programmer can create these free-form instructions and store them in Robot Studio as a library, and then bring them in whenever it's required. In this next slide, you see an example of shape tuning. On the left portion of your screen, you see the program that the robot is performing out of the box with no tuning. And of course, the shape is not very circular and is not in the desirable size. So therefore, with the advanced shape tuning, and after all the iterations I explained earlier, we have the ability to achieve better path geometries, and the circle expands itself. It tries to be more accurate based on the nominal program. And the ILC that I explained, it's trying to make the shapes more circular and avoid eggs. Here you see a couple of screens of Robot Studio Cutting Power Pack, which is the 3D environment with automotive parts and a lot of different features that are part of our libraries and CAD models. So once the programmer is ready creating these programs, he can hook up his computer to the real robot and download these programs directly into the real robot in the manufacturing floor and be more efficient. Process simulation can be done. You see the paths, you see the targets, and you can calculate the cycle times in Robot Studio. In path optimization tools, you see here an example of a circle where on the right hand of the screen you see a lead-in line, which is what the robot is actually performing on the manufacturing floor, and it's plotted into the offline environment when the computer and Robot Studio are hooked with the real robot on the floor. And it's difficult to see right now with a small screen, but if you get a little closer look, you see an overshoot where when the robot is coming from the lead in and starts to reach the shape, where the robot decelerates to try to achieve the circle line, and then it has to accelerate immediately to start cutting the circle. Well, that overshoot is plotted in Robot Studio, and we can therefore do just some optimization and evaluate if we are to decrease acceleration, deceleration, or decrease the processing speed. I mentioned earlier the importance of the booth, the light tight enclosure, which, by the way, the ABB offer for the light tight enclosures complies with the CDRH certification or filing, which is part of the Food and Drug Administration requirements in order to operate lasers in the United States of America. So our enclosures are compliant to these laws. And it's, of course, sized to fit the robot positioner, different sizes and configurations, and is perfectly interlocked with the safety of the robot with dual chains. We have the ability to add exhaust systems. We can deliver the exhaust system, or we can just give you the hood opening for you to hook up the exhaust system from your factories. And of course, all cable management is going through the pallets. This is a modular cell where you can, you see everything is mounted on pallets. It helps ABB to be faster in recommissioning, and it gives you the ability to relocate the equipment as it's already at your manufacturing area. If we are to add windows for people to see what is happening in the booth, we can offer laser safety rated windows, or we can offer vision systems, cameras with monitors for the operator to see what is happening inside the cell. In this next slide, you see two videos. One is a real robot in the main screen, and in the lower bottom on your right, you see a Robot Studio simulation, which is actually the real offline programming of this project in specific. So you can really say that what you program is what you get, especially if you use calibration tools, automatic calibration tools like Bullseye, and downloading the programs into the real cell. And here you start seeing some examples of the laser cells that we in ABB deliver for both cutting and welding. This is an example of an R positioner. And next comes a C positioner with no axis of manipulation of the parts. This is just an indexing table. And then comes the K, where we are manipulating the part, and it gives us the ability to introduce larger parts with heavy payloads. And we can also add a second robot if the application requires. So we can have two robots working on the same station and even share the laser beam. That doesn't mean you need two laser generators. You can share the beam between those two robots and save money on the second laser. And last but not least, the two fixed station cell, what we call the laser U2, laser cut U2 or laser weld U2, depending on the application, which, by the way, is the same cell regardless of the process. What it changes is, of course, the laser head, which is different for welding and cutting. So if I am to summarize in a few words, robotic laser processing gives you the ability to go down to 35% savings in the capital investment with a higher manufacturing flexibility. And all that is basically thanks to the software technology of ABB, of what I have been discussing during this presentation. So I'd like to thank you all for participating today with us, and please feel free to contact us at any time, and we will be able to have a look at your projects. Thank you very much.
Jorge, thank you very much. That was a very comprehensive presentation on ABB's capabilities, and I know it has engaged our audience because we have received a wealth of questions. I'm not sure we'll be able to get to all of them during the time remaining to us today, but we will attempt to answer them, and so I'll read some of them off here for you and Jeremy to answer. One of them that I see here is, how do you control spatter when either cutting or welding?
Spatter, by nature, is a byproduct of laser processing, but for cutting, usually the dross or spatter is going downward. You really can't control it other than having your tooling deflect it such that it's not going to interfere or be hazardous to your tooling cables or I/O cables. For welding, if you have good fit up, metal fit up, you can have minimal, say, spatter or expulsion while you're welding and processing. So I guess the answer to that is you try to design your tooling such that it either eliminates it or deflects it from being a hazard to your process.
All right. Here's sort of a general question, but it's a good one. What is the footprint of the ABB laser robots?
It depends on if it's the IRB 2416 or the IRB 4416. I mean, to give you some rough dimensions, just at the robot base, which is the floor footprint of the robot, the IRB 2400 is about 700 millimeters by 600 millimeters at the robot base. And then if the 4400 is about 900 millimeters by 600 millimeters at the robot base. But the in-depth information can be received at ABB.com, and if you search for the IRB 2400, there's data sheets there for the IRB 2400 and the IRB 4400, which give you full work envelope specifications, payload specifications, and footprint.
We're also able to provide information about the cells, the footprint of the cells, because we have a standard range of cells.
Okay. What tolerance can you hold a 10 millimeter gauge hole to?
Since that's a pretty process specific question, I can tell you that we have customers that are running 4-way and 2-way holes that have tolerances of 0.1 on 6 millimeter to 10 millimeter holes, and they're running in production right now.
Okay.
Without doing a lab test for the person who presents the question, I couldn't tell them specifics.
Okay, there looks like they're talking about a hot stamped part here. That will give you
those tolerances were from a hot stamped part.
I'm sorry?
The 6 mil to 10 millimeter hole with 0.1 millimeter tolerances is something that we achieve currently in production for suppliers and customers of ours.
Okay. A software question here. Can you use Mastercam to program the paths?
Currently, it's not supported. We use the Robot Studio Cutting Power Pack to do all of our offline programming for paths on parts.
Okay. And a question that I believe was answered during the presentation, but just to make sure that it's fully understood, where is the laser light generated? At the head, at a fixed point, and carried through the fiber optic?
Well, that one is the nature of lasers. It depends on if he's saying where is it generated from, it's generated from the power source, which is usually mounted externally and then delivered fiber optically to the processing head, which then the laser then travels through the collimating optics and the focus optics out the head to the workpiece. So I guess to answer the question, in the booth, it comes out the laser head, and then focal range is dependent on the process.
Okay. What laser parameters are you able to control via the program of the ABB robots?
That's a good one. Currently, we support with robot wire cutting. You got power. You can control power, and if you need to control with, for say, like the IPG laser, you want to write a user-defined program where you're doing modulation or other things inside the program. We have the ability to trigger programs to the IPG power source, or with rope and Cinar, you can do duty max and duty min, so you can do pulsing based there. You also have the ability through I/O to do ramping and gas, piercing time, piercing height, cutting height, speed. There's a whole bunch of parameters above and beyond that we can provide a cut sheet with robot wire cutting and all the parameters that are inside our cut data.
Okay, thank you. Here's another one. How portable is the setup? Is it easy to move for a large product?
I would say that we've taken one from our floor and put it back up and running in a production environment within 3 days, but that's depending on the level of commitment to the installation.
And if we compare that to a 5-axis machine, is nothing in time. So, as Jeremy already mentioned, we just unplug services, divide pallets. We have the ability, or our pallets are modular, meaning that the booth and the enclosure are attached to the pallets, and it's easy to move them with a forklift, reattach those pallets, reattach all the services and connection points, and start producing again. While a 5-axis machine, well, you will need a lot of equipment and time.
And another, can the same cutting head be used for laser cutting and welding? And what kind of cut tolerance if it's capable of handling both?
In my experience, Jim, I've never used the cutting and welding head for the same process. Usually it's process-dependent heads. I know that there is, if the question is referring to tool changing, we haven't done tool changing where you can do 2 processing heads in one cell. But that was where you could get in contact with LaserMech or Precitech or one of the other head manufacturers and see if there was a solution for a head, and then we would be more than happy to integrate that into one of our standard solutions.
So that's a question for your partners then?
Correct.
Yes.
All right. What are the limitations to what joints this robot can weld?
I missed that one.
I'm looking forward to.
Let me see. What was the question again, Jim, please?
What are the limitations to what joints this robot can weld?
Well, I think that is a difficult question to answer without seeing exactly what the part looks like and what the part is. We're talking about a very specific process with laser that depends on many factors like material type, material joints, type of joints, configuration, thickness, gas to be used, etc.
Optical tracking, such as seam tracking.
Yeah.
I mean, typically we do lap joints, T-welds, butt welds. I mean, but once again, as Jorge said, it depends a lot on the application itself.
So this is very much an application-specific question then.
Correct.
Have you ever installed an application for a heat exchanger tube to tube sheet welding? Here's another very application-specific question.
Yeah, we have not delivered such an application like that, but of course we would be happy to look into those questions separately.
All right. For laser seal welding, how accurate can the system track a weld seam in a 1/2 inch diameter circle?
Yeah, that's also very application dependent. And is more a question for our partners with the heads and scanning equipment.
Okay.
We are delivering motion through our robots, and these questions have to be turned into companies like Precitech, LaserMech, Trump.
So this would depend at least in part on what type of material you're working with, the thickness of the material, and so forth.
And also what the customer would be willing to spend, because there is solutions for optical tracking in addition to robotics. So you have the flexibility of a robotic solution, and then you add technology on that to help maintain even a higher level or tolerances that you require.
Well, that leads us right into the next question that comes up. What is the price of the robot system?
Yeah, well, we would like to see this.
Sorry, I'm in the wrong place. Sorry about that.
We would like to have this question treated separately.
Okay, so it's really an individual application. It's what the customer would want
Yes.
to determine
Yes.
the price then.
It's actually an ABB policy not to discuss financial aspects on an open line like this.
Okay, I can understand that. Well, at that point, I'm afraid we're going to have to close this up. Our time is almost gone. All the unanswered questions will be passed along and replies sent via an email. As Jorge proved with his presentation, robotic laser cutting and welding is a very fertile field for manufacturing. Throughout the rest of the year, Manufacturing Engineering Media will be taking a look at some of the component parts of these technologies. For instance, the editorial lead in the August issue of Manufacturing Engineering will focus on automation. In September, robotics and automation will be covered in a feature article. And the November issue will have a piece on advancements in lasers. We thank you for joining us today, and we hope you found the presentation informative.